so my name is Kiara, and today I'm presenting Lab 1, Electric Forces Between the Tapes, and I'll walk you through my measurements, force balance, charge calculations, and how many electrons were actually transferred when I charged the tape. So in this lab, we experimented with pieces of tape to determine the amount of excess charge and their interactions between the pieces of tape. And so part 1 was done physically with tape and materials, and then part 2 was done with the computational model through GlowScript. And so, like, a brief overview of my results. So the charge on each tape, my tapes, were determined to be around 1.16 times 10 to the negative 8th coulombs, and the number of electrons lost by each tape was around 7 times 10 to the 10th, so a super big number. And so these were some of the fundamental principles that I used. So Newton's second law, force is equal to change in momentum over change in time, and also mass times acceleration. And I also used the force of gravity, which was also equal to mg in this case, and Coulomb's law. So the charge, the two charges, and the distance between the two, the magnitude of the distance between the two squared, and times k. And in this case, k was 1 over 4 pi epsilon naught. So the initial conditions of my tapes, well, I'll show you the video here. It's like a little stop motion of what happened. So the length tape was 0.2 meters and the tape width was 0.02 meters. So multiplying them by each other, I got 0.004 meters squared. And the mass of the tape turned out to be 0.198 grams, or 1.98 times 10 to the negative 4th kilograms. And so I found the atom area by squaring 1 times 10 to the negative 10th, and the number of atoms, which I divided the tape area over the atom area, and it ended up being 4 times 10 to the 17th atoms. And so this is what my parallel tape model looked like. And so the system is the tape on the bottom right here. It's kind of hard to tell, but it's tape number B. And the surroundings was the tape on the top and everything around surrounding it. And so I measured the distance for them to be 0.025 meters. And so I'm going to get into my calculations. So the force due to gravity is mass times gravity. So in this case, I used my mass found from the other section, 1.98 times 10 to the negative 4th times 9.8, and I got this value right here. And then I, since the electric force has to be equal to the force of gravity, the magnitude basically is the same. And to find the electric charge itself, I set this equation equal to each other, and in this case, the distance is 0.025 meters, and k is 1 over 4 pi epsilon naught. And so dividing by k, multiplying by d squared, and square rooting that, I ended up getting a q value of 1.16 times 10 to the negative 8th. And so now with these values that I've calculated due to my experiment, the number of electrons lost ended up being 7 times 10 to the 10th, which I found by dividing the charge of the tape divided by the charge of the electrons. And so the ratio found was also the number of atoms over the number of electrons. And so through my calculations that I showed before, 4 times 10 to the 17th and 7 over 7 times 10 to the 10th, which I ended up getting 5.7 times 10 to the 6th. And so now getting into the GlowScript code, what I ended up changing were the values up here. This is what my code looked like, first of all, and the parts that I changed were up here according to my values that I used. And through this code, when I ran this code, I ended up getting a result that looked like this. And so the force on the gravity was negative 1.96 times 10 to the negative 3rd, which was very close to my values. And the charge on the tape was 1.16726 times 10 to the negative 8th, which was actually also very, very close, very slight errors in the hundreds and thousands. So why were there some errors between my values and the GlowScript code? There were obvious assumptions made when we were doing this experiment. So I assumed that the long piece of tape is a point charge, and in reality, it is not. The charges are distributed throughout the tape. And I also assumed that each tapes have equally distributed charge, and the chances are they might not be. I also also assumed air resistance, friction, as well as other electric forces in the surroundings to basically not exist. And therefore, the charge was lost, probably due to a system that's not fully enclosed. And so, now getting into the discussion portion, what would happen if the electrons and the protons had inverse charges? So, mostly all the observations would remain the same. But the only thing that would be different is that the charged pieces of the tape would be negative, and they would still repel each other, like shown in the tube bridge system where one kind of floated above the other. But they would still attract the positively charged pen. And so why is it important to handle the tape as little as possible? It's really important to do this because charged tapes begin to neutralize when like encountering my hands or like other objects around it. And so there's like a transfer of electrons that happens there, and they begin to neutralize. And they try to gain the electrons that they lost when I pulled apart the tape. So it was really important to be as quick as possible and not have it touch many things in the process. Thank you.